Hello, my name is Joe Cassette. I'm a high school physics teacher from Minnetonka, Minnesota. And one of my main passions in teaching science is providing students with opportunities to really investigate and dig into science through the lens of the nature of science. And one of my favorite ways to do this is providing opportunities through puzzles and games that students are interacting with each other, but also with challenging tasks so that they can really get the understanding of what science is and what that process looks like. All the different materials that I'm presenting in this session can be found at this bit.ly link. And my Twitter handle is here. It'll also be posted at the end if you want to follow me for more ideas like this. So to get into this, I want to highlight just the general agenda of what I'm going to look at in this 25-30 minute video. First is just talking about what the nature of science is. What do I mean when I'm using those words? And then there are three main tasks that I use in my classroom, different games and puzzles that really get at some of the core concepts of nature of science and provide students with opportunities to really dig in and be hands-on and investigate some of those skills that we really want them to gain in our classroom. So we'll talk about something called the game of science, inquiry cubes, and a task called missing piece. At the very end, I'll describe where all of these materials can be downloaded for free from my blog, and then just discuss a little bit about how all of these are connected through that umbrella of nature of science. So, to get started, what is the nature of science? Well, there are lots of different descriptions of this. This shows up pretty heavily in the Next Generation Science Standards, NGSS. It's also posted on the NSTA, the National Science Teaching Association website, and they have a list of guidelines that you can find about nature of science and what it is. So to highlight some of those key things, here's just kind of the snippet of some of those main core concepts that are part of this general umbrella of NOS. So things like using investigations with a variety of methods, so finding different ways to look at a problem, or finding empirical evidence and using evidence to present your reasoning and understanding. Science is open to revision in light of new evidence. That's very important. Creating models, laws, and things to explain phenomena. It's a way of knowing. It assumes consistency, is ultimately a human endeavor, and it addresses questions about the natural and material world. And this shows up in all of the things that we do in our science classroom, but sometimes it's hard for students to see exactly what all of these are. And sometimes, honestly, in the things that we do, some of our basic labs and investigations, they don't get the opportunity to dig in all the way in some of these. So I like to provide my students opportunities at the very beginning of the year instead of just a standard icebreaker. Give them the opportunity to investigate and dig into this as their challenge and opportunity to work together. So let's look at a couple different examples. Through this, I'm going to provide and present these first as a teacher to students to kind of model how I would do it in my classroom and give you, the viewer, the opportunity to see what this looks like from the student point of view. I call that the learner's stance. And sometimes it's really powerful to just have the opportunity to investigate and really engage in the task as if you don't know the answer, because that's the system that our students will be in when they do things like this in our classroom. So the first task that we're going to look at, the first game, is called the game of science. It's learning the rules through observation. And I present this to my students through a story. So when I was growing up, my grandparents were big card players, and they were both they immigrated from Canada, and they were French Canadian. English was their second language, and they lived in Michigan. So the big card game in Michigan, so you may know, is a game called euchre. And euchre, very similar to 500 or another trump taking game, is a game that they just loved, but they could never really describe to me how it is they were playing this game, and I really wanted to learn. So as I was watching them, like, I would ask questions, but they didn't really know how to describe exactly what they were doing. They just knew how to play the game really well. And I learned that game not necessarily by reading a rule book or having them teach me all the rules of the game. I learned the game just by watching them play. You see things happen and you kind of make a note of it. You see it happen again and you say, oh, that must be a rule. And eventually you see enough things happen that you start to piece together, here are things that you're allowed to do. They're doing it this way because that's their goal, or they're not doing it this way because they can't do it that way. And some things, as simple as how many cards there are, you can observe very quickly. Some things, as far as all the different ways that you can score, you need to observe for a while to start seeing all of those different scenarios come about. Well, in this particular game, we're not going to play euchre, or we're not going to do one of those obscure Olympic sports that I'm usually watching and learning the rules, like handball in the moment. We're going to play a game that I found in the back room called the Game of Science, and we have a playing board and we have some pieces that every group gets. It looks something like this. And then we also have access to a couple different game histories. So if you ever looked at chess, one of the things that chess players do is they can record the different moves that happen in a game. And some of the biggest games in the world of chess have been recorded in this way, and there are books and books of chess games from history that you can go back in and read all the different moves that happen to recreate these games that took place in another time. Well, this game is similar. You can recreate from a history something that has happened in the past. And we don't give the opportunity necessarily to watch them play, but we can recreate the things that happened to try to figure out what took place in that game. Now, some of the main things that you're going to want to look for is, how does the game start? What are the things that you can do or can't do in the game when you're moving your pieces? And what is the goal? What are you trying to do in that game? And I have students go through this process and try to recreate what the rule book would say. So if somebody just received that list of rules, that would be enough for them to play this game. Now, for us here in this learner's dance through a video, it's kind of challenging to do it this particular way. You don't have the pieces to move around. So I have created an animation of a couple different games that have been played. So I'm going to play that animation for you right now. All right. Red wins. Congrats, Red. So as you can see, riveting game. Um, through watching, you can start to piece together pretty quickly what some of the rules might be. Whether it's as simple as, oh, I think that all the pieces seem to start in those empty squares. That's where you put them. And you can put them in this order, 1, 2, and 3, so on. You might notice what it looks like the objective is. Red won as soon as all of those red pieces made it off the board onto those triangles. And you can see where they are going. Red isn't trying to get to the triangles on the left. They're trying to go all the way down to the bottom. I usually play another game for them, or I give them another opportunity to see a different game being played, because sometimes something could happen in one game that doesn't happen in another game. And students have to decide, is this not happening because it can't, or because they don't want to? It's not good strategy. For example, can the pieces move backward? Or are they not allowed to? Or is it just a bad idea? Like, why would you go backward? So we have a discussion of, is that a rule? Or is that just like a circumstance in the game? Kind of a coincidence that you never see it happening. And we go through this, create all of these rules, and come back together to discuss what we think the rules of this game are. And students are always really excited to try to share a rule that they think they found that nobody else has found. Something like hyper specific to their experience in going through this game. Now, putting our teacher hats back on, this provides a really great opportunity for students to discuss what science is and how this is connected to science. And depending on how experienced students are, like my seniors in IB Physics, in, investigate and really relate to this in a different way. But there are a lot of different pieces, nature of science, that shows up. So one is, rules are often grounded in past experience, that we are using our understanding and our observations and the evidence that we see around us to create these rules. That this isn't something that's given to us, we are experiencing things. We're seeing how a ball rolls down a ramp, or we're seeing how a plant grows. And we are discovering, based on that experience, certain patterns that are always happening that we can consider rules. Now, those rules can only define conditions that we have observed. There are many times in science that we observe something new. Uh, there was one of the game histories that something surprising happens. A piece isn't able to move, it's stuck, and they lose their turn. All of a sudden, students see something that happened there that they hadn't seen in the other games, and they have to rewrite their rules. Now, something that was kind of ambiguous and unknown is now known. They saw it happening. That happens in science too. That we can have a pretty good theory and even a description of exactly how something is happening. For example, Newtonian physics. And then something happens outside the bounds of something that we really thought we could observe that breaks our rules that we wrote. So those rules need to be modified or extended beyond what we had initially defined to give us a better understanding, a more universal understanding of something that's happened. Now, there's no way of fully confirming our predictions. It is hard to prove something 100% correct. You can prove it wrong. You can set up tests to say, I wonder if this could happen. And then you see it doesn't happen, or in that situation, all of a sudden they can't move. And then that's enough evidence to rewrite the rules. But it's hard to 100% confirm because we don't know if we have seen all the situations. Or we don't know if something that we're seeing is a rule or a coincidence. And we can use these rules to play the game ourselves. One of my favorite parts of this task is that students then can go back, use the rules that they wrote, and then play the game. They can actually play each other and have a little tournament using the rules of this game that they had never received before. They learned the game entirely by watching it be played. This happens in science as well. We can use our observations to create a set of rules and expectations and patterns, and then use those patterns and rules to interpolate and understand something that we haven't seen yet and make a prediction of something that maybe could take place, but we haven't had the opportunity to try it. And that's a good way of testing our theories too, to see if the theory itself is enough to predict some unknown. All right, going on to the second challenge or puzzle or task, something called inquiry cubes. This is actually my first day in the classroom. This is what I start with at the beginning of every year for my 9th grade physical science class. And inquiry cubes is all about patterns, and very specifically looking at one of those nature of science things. Can you make a prediction and test that prediction? So I start off very simply here by showing students a 6-sided die. There's an animation here on the slide. This is actually the one that I use in my classroom. It's pretty standard. There's one key difference. It's missing a side. In this animation, that's the side that you're not seeing because it's pivoting around that axis. But we have seen one of these before. We can use our prior understanding, our prior experience to predict what we think is on that 6th side, what's on that missing side. Now take a minute to look at it if you haven't already. Try to predict what's there. I usually have my students kind of hold on to it in their head, and then 1, 2, 3 will shout it out, and of course it's 4. It's missing the number 4 because we have seen this before. We know that it has the numbers 1, 2, 3, 4, 5, 6. That's what we would expect, and we can see all the numbers that I listed off except for the number 4. You might also know, and students often sometimes know, that there is another pattern that's built into these standard playing die. It's that opposite sides always add up to the same number. So if I look at this side here, number 1 is always opposite number 6, and number 5 is opposite number 2. 1 and 6 is 7, 2 and 5 is 7, which means even if all I showed the students was a 3 and then the opposite side is missing, that's enough to know that the opposite side must be 4. So it's good for students to see that there's more than one pattern sometimes built into something, that the deeper you look at it, you might notice things that you didn't before. Now, for this task, we're going to do something that's a little bit more involved than that 6-sided playing die. Instead, there are a bunch of different cubes here that have different patterns on them, and they have more than just one pattern. There's 5 different patterns that are happening simultaneously, but all of these cubes are missing a side. So here's an example. These are all foldable cubes that you can print and fold uh, into that cube and tape them up. They work out really well, but it's a lot of work to put them together, and then they're not super sturdy. Somebody could crush them just by putting a bit of pressure. So I've gone toward making these. This is my big version where I just cut up a 4x4 post. They all have a missing side though, so you see them there. These small ones are actually adorable. I love these things. They're little 1-inch cubes that I printed it out on an address label. So you can get 3 per address label, and then they're just stickers and they stick on already. And I was able to print them out and make a bunch of them really, really quickly. And that's small but sturdy. And it's enough that students can really physically manipulate these and really engage with that in more of a hands-on kinesthetic sort of way. And again, their task is to try to figure out what's missing on all of these things. During the pandemic, when we were all online, of course, I couldn't do this small physical way of doing it. So instead, I sent them links to virtual cubes that I made up and posted as a 3D model that you can actually just click and drag or swipe around and physically just move the model of the cube. So you can do the same thing that you would do here physically, just through a screen. So it's another option. But with all of these, the task is to try to figure out what's on the missing side. I let students self-select which level. They do get pretty challenging there at level 3, and they self-select, and when they're done, they turn it in, and I'll bring one back, or they get a new one, and they can keep working until the very end. And I tell students that I will be their check. That if they think they have a theory, they need to write it down in some shared space between them and their group, and I will come around and I will give them feedback on if they're right. But the challenging part is the feedback that I give is very specific. I will say that it is 100% correct, which means it matches the missing side that I have on my answer key, or it is not 100% correct, which means they could be missing one part of the pattern and I won't tell them what part of the pattern is, or even the fact that they're only missing one thing. It's the same feedback as if they were missing all of them. And it really requires them to go back in and look at it together and try to evaluate what it might be. And it can be challenging and it can be frustrating. And we have a great conversation of what it means to be working persistently. There's a great YouTube video, a TED Talk about grit from Angela Duckworth. And just that conversation of what does it mean to hit a challenge and keep working through it. By the end of the hour with these different levels, every group has the opportunity to be successful in at least one of the cubes. And some groups that are flying through it, they have more things to do. So they aren't necessarily stuck just watching or waiting. There's always something for them to work on. Now, a more current project, more recent, is a level unknown. So that's this cube here. It's easier to see on this animation. And this level is one that I actually do as its own separate task, usually after they've had an opportunity to try these ones that I showed before, levels 1, 2, and 3. Level unknown is designed in a way that it has more than one answer. And they need to decide on an answer and defend it to their classmates. So I'll take a simple one, for example, here. If you look at the number in the top right corner, you'll see numbers 4, 5, 6, 7 on the top, and 8. Now, 4, 5, 6, 7, 8, obviously there's a pattern there. And there's a missing number. But is that number 3? Does it start at 3 and go to 8? Or is that number 9? Does it start at 4 and go to 9? So there's a bit of ambiguity there. That pattern just so happens to interact with another pattern. That number corresponds to the number of letters of the animal that's on that side. So for example, chicken up here spiraling on the top has 7 letters to correspond with that number 7. So depending on the number that they choose, that will affect one of the other things that they choose. It'll affect the name of their animal. And their goal, what I tell them, is to try to come up with a pattern that they don't think anyone else has. In the end, for this cube, I don't tell them an answer because there isn't one. The answer is whatever they're able to defend and talk about the patterns, and they can try to push back on each other if they don't think that that pattern holds true. But usually by the end of the class, I have 6 different answers that are all equally correct, and there's a bit of science in there as well. So some of this nature of science connection, there could be multiple possibilities that sometimes we just don't have enough information to know. And the best that we can do is to narrow down our list and say, from the evidence that we have, all of these things are possible. We need more data to go from here. Sometimes that pattern depends on your perspective. So you might see something from your understanding, and somebody else might see something else based on their own different interpretation. You can't always test your theories. So in this particular case, when I'm having them check it with me on the first day, I have different goals than when they don't really ever check it on that level unknown. So sometimes you have a theory and you can't really test it out because it's theoretical. And a lot of astrophysics and cosmology is currently in that state. And nature sometimes limits your options. So, for example, that example that I gave with the number and the number of letters in the animal, you could, in theory, totally do 9 because that fit that number pattern. But it's a lot harder to come up with an animal that has 9 letters than it is to come up with an animal that has 3 letters. There's a lot of those. So sometimes just understanding that says, well, technically both are possible, but this seems more likely because we have all of these other possibilities that this could be versus the 9. All right, the third task that I want to look at here to talk about nature of science through puzzles and games is something called the missing piece. And what I love about this task is it directly ties into a conversation that we have about the periodic table. So very similar to the inquiry cubes, the goal is to figure out what's missing. Now, instead of giving them a cube where they have 5 sides and they're missing the 6th, I give them a deck of cards, and the cards have all the cards in the deck except for one. One's missing. And if I give a standard deck of 52 playing cards, you could figure that out. Even if you didn't know what those were, if you had never seen a deck of cards before in your life, you could see patterns. You could see that there's hearts, there's clubs, there's diamonds, there's spades, and if you made piles, you would notice that one of the piles is one less than the others. And from that, then look through each of the piles and figure out, okay, which one do they all have, but one pile is missing? And you could work your way through it. For this task, I give them a deck of cards that they've never seen before. It has patterns, it has shading, it has numbers, and through this, their task is to look at what they have to figure out what they don't. And that task is hard because they don't have that built-in knowledge to understand what this is to begin with. And there are a couple different ways that they go about that. One of the biggest important things that they need to do is they need to start organizing. So just looking through the deck, they could spend all day just memorizing these. Doesn't do them any good. So what I advise them to do is start to lay them out. Group things based on patterns that they're seeing. So here you can see that they are grouping based on the number of notches, and they're also kind of trying to keep shading the same. They're coming up with these diagonal patterns. Another group was doing a similar diagonal thing, but they were kind of squishing them together a little bit more. Another group still was going for more of a grid pattern. And when they did that, they noticed that there was one missing spot in their grid. That everything was organized based on patterns. They saw a row of stars, row of dots, 2 stars, 2 dots, 3 stars, 3 dots, and there was one 2 dot that was missing. Well, that was the missing card that they were looking for. So from that missing gap, they were able to tell me, they wrote on a piece of paper exactly what that missing card should be. And of course I had it in my pocket that they could see that piece. Now, this is a pretty easy thing to print out. This is actually based on a deck of cards that I had seen when I was in grad school. That's a lot harder to find, so I just made one for myself. And the deck of cards is typically in color, but my printer at school isn't in color, so there's a grayscale one as well that you can just print it out and then just hide one of the cards and give them the rest, and it's up to them to figure out what's missing. Another version of this that some people may have seen is something called Periodic Aliens. This is an awesome activity that's online that I modified a little bit and posted my version of. And it's a very similar thing that I give students a group of aliens on cards, and their task is to figure out what the missing alien looks like. And of course, they had never seen this deck of cards before. The only way that they can figure this out is by starting to organize it. When we were virtual, I made this on a Jamboard. So this is what the Jamboard looked like. It had a bunch of alien cards that they could move around. And I made it a little bit smaller so that they could do it in a screen. But when they organized their cards based on certain properties like the body shape and design or the number of fingers, 1, 2, 3, 4, 5, they noticed that there were some gaps, and they had to take those gaps and figure out what the missing pieces would be. This is then those missing answers. What's great about this task is you can then extend it. That it feels like this should be the end, and my students felt like this should be the end. They solved the task that I wanted them to solve, but of course, just like any task like this, some will solve it faster than others. And I want to give those faster workers something to then continue to challenge themselves on. I don't want the prize to be that they're just sitting around and making it feel like others are going too slow. So when they're done, I extend the pattern, and I'll put post-it notes or here on the Jamboard have some extra cells that the task is then, okay, if this is a pattern here, what happens beyond that table structure? Like, can you continue this, or even missing a couple columns, you know what that one would look like based on what patterns you think you're seeing going vertically and horizontally. And of course, you can fill them out. Some of them are ambiguous. You need to design your own pattern here. You might not know exactly what it looks like, but that's up to you. Yeah, you're kind of the discoverer of these aliens. This is what it looks like in person with these cards and a bunch of post-it notes that I've just added kind of on the perimeter that they present to me. And then if they look okay and they're able to describe their pattern or defend their thinking, I'll give them a couple more post-it notes and they keep going. So through Nature of Science, there are a couple pieces here. Sometimes organization itself can lead to discovery. Sometimes graphing data and seeing a trend, or in this case, just grouping it based on properties, highlights there are some that are missing or some other patterns that you weren't seeing necessarily before that organization. And this has a direct tie-in that I use as well. Mendeleev, when he first presented his periodic table, wasn't well known for being the first person to organize it. Other people had done that. His big thing was he used his organization to predict something that had never been discovered before. He discovered, theoretically, gallium before anybody had physically found it. And he did that based on the patterns he saw in his organizational structure. So as I promised, all of this stuff can be downloaded. There are blog posts on my blog that detail all of these things that I described in this video and have ways that you can download these materials or use the virtual versions that each of these tasks have in them as well. And then if you ever have questions, you can always reach out. My Twitter is there. You can also send me an email or reach me directly through my blog. And I'm always happy to help out or be a thought partner if people have questions or ideas for similar tasks for them to run in their own classroom. So if you have any questions, feel free to reach out. And I hope everyone has a great start of the year and opportunities to embed nature of science into their classroom, no matter what type of science they are teaching.